All right, everybody. We're done topic one now of mechanical systems. And so here's just a quick video review of some of the key things that we've covered. So this unit's very different. It's a physics unit. So we're talking about things like when you have work to do, right? Or if you're moving heavy loads or lifting boxes or creating the Great Pyramids. So all of these things require work, which is some kind of a labor to move a load. So load is kind of a science word for just some kind of a heavy object. And so it has weight, and likely we need a machine to help us move it. Um, we also usually need some kind of a force, right? So whether the force comes from us or it comes from the machine, whether we apply some small force to a machine and then it multiplies it to do the rest of the job, right? All of that is force. So force is kind of like the effort that you're putting in to do the job. A good example is kind of to think about how you would lift or move heavy things. So how you would dig a bunch of holes, let's say for planting trees, or how you would move all your groceries at once, right? Or how you would help someone that can't walk to get up to their front door. Okay, so these are all examples of work, right? Where you need to put in a decent amount of force in order to make something happen. Okay, so yeah, just kind of keep some of those things in mind. And we started with simple machines. Ooh, here's a picture for you, if it'll pull it up for me. Simple Machines 101. There you go. So we talked about a couple different things. First off, we talked about a lever. So a lever is almost like a straight flat board, but we kind of like counterbalance the weight with a lever in order to make it do work. So we could think of something like a fishing pole or even a seesaw, a can opener, like a manual bottle opener. The levers can change depending on where the load is, where the fulcrum is, which is just kind of like the pivot point, and where the effort is put in. But levers work the same. Okay. Pulleys are basically when we have a rope on a big wheel, and if we pull down on one side, it lifts the other side. So you can think of things like weight machines, right, that have a lot of resistance, but you're pulling on the pulley handles to move the weight up. This is usually for things that we want to move straight up. Also, things like window blinds, right, are operated on pulley systems. Inclined plane is basically just a ramp, okay? But because it's at a slight angle, we do end up going a farther distance, but we use a lot less work to get to the top. So this is considered a simple machine because it's a lot easier for us to roll or move heavy loads or items up here on a ramp than it is to lift it from the bottom floor to the top floor, okay? So yeah, inclined planes you can think of just like a regular ramp on, let's say, a moving truck or even outside a building, like wheelchair ramps maybe. You can think even about like stairs and roller coasters use inclined planes. And then we have a wedge. So a wedge looks like two inclined planes put together, but because they're put together, they have a sharp tip. And so their job is to kind of, I don't know, separate things, right? So we can think of things like an axe or a knife, scissors even, how the two blades come together. So that's considered a wedge. And it does, again, the work for us. It would be a lot harder for us to cut our food with our bare hands than to have this machine that does it for us. And a screw. So a screw has a bunch of grooves around a cylinder. And so we can use screws as ways to fasten items together. We can also use it in something like Archimedes screw, where we can use the grooves to pull things up. Okay. Yeah, like even a good example of a screw is like the lid on a jar, like your peanut butter jar, because it keeps the contents in and it's a simple machine. And the one that's missing from here is actually a wheel and axle. So we use wheels on, which is kind of like our pulley without the ropes, right? So we use wheels on lots of different machines, things like skateboards and bikes. But when we think about using them for work, we use them on wheelbarrows and wagons and shopping carts at the grocery store. So all of these things make those jobs easier to carry and move loads around. All right. So if you combine two or more of these machines together, you get what's called a complex machine. So complex machines have many simple machines working together to create a system. Okay, and so we can see here that the bike is moving because of a variety of simple machines together. So we have levers in the brake handles, right? If you're going to pump the brakes, you pull on that lever and it squeezes the brake pads on the back wheel to stop the bike. We also have levers in the pedals here that are moving. We have a pulley in the chain that connects the pedals to the wheels. And of course, we have wheels. We also have screws that are connecting all these pieces together. Okay. Another example of a complex machine is an escalator, right? So this one would be an inclined plane because it's on a ramp, and it's also on a pulley system because these stairs get pulled under and then come back up again. So a lot of our machines are considered complex machines. That combine a couple different simple machines. And so we would also say that these machines have subsystems. So again, for example, in the bike, even though this bike operates as one whole system, it has subsystems or subunits, smaller units that work on their own. So like the pedals and the gears would be like a gear system, right? So if you were going to shift gears on your bike, that would be one system of the bike. And if you were going to brake, right, at the top, your braking system would be a different part of the bike. So within our bike, we might have like a steering system, braking system, and a gear shift, right? So those are all considered subsystems within this complex machine. Okay. Now, when we look at what powers machines, this might be something a little bit new for some of you. I know you talked about energy last year in heat and temperature. So you talked about things like thermal energy. You maybe talked about electrical energy a little bit. I know you talked about light energy when you talked about plants. And then we also might know some of these other ones. So it's important to know that not all energy comes from electricity. That there's many different forms of energy. And what we actually see in this picture, this is a great picture, it shows energy transformation. So know that energy is not just poof created, it's transformed and changed and shifted. So for example, like electrical energy, right? We can plug in our stove and we can turn it into thermal energy, right? Or we can take chemical energy like gasoline and we can put it in a car to create mechanical energy. Okay, so mechanical energy is any energy that's moving. And we use mechanical energy quite often from our own bodies when we're using machines. So if you're, cutting up firewood with an axe, that's mechanical energy, the energy of movement, right? If you're riding a bike, you're using mechanical energy. And then where does our energy come from to move these machines? Well, our energy comes from chemical energy, from food, right? Because food is basically chemicals or proteins that our bodies break down in the digestive system and then they store for later. And every time we need energy, our body breaks down some more of that glucose and feeds our body, right? So we have things like, chemical energy, mechanical energy, electrical energy for any machines that we might plug in. Yeah, and then we also have other alternative energy sources. So these are all mostly renewable resources. Nuclear power isn't renewable, but solar power is. Hydroelectric power with the water, right? Wind power. Geothermal power is the heating of the earth or the earth's inner heat. And biomass is actually when we burn living things, and so we use their original compounds kind of to power things. So yeah, these are all different forms of energy, and these energies can power machines. So it's important to just kind of be aware of some of these examples of energies, because I will be asking you, what powers a skateboard? Well, a skateboard is mechanical energy. You have to move it, right? Or what powers a solar light? Well, the sun or solar power, right? Or what powers a water mill? The water that's running through the wheel, right? What powers a battery? Chemical energy, right? Because it's chemicals stored inside the battery. Okay. And then the last kind of thing that we talked about in this unit was transferring energy. So this is an example of a linkage. So a bike chain is a really good example of how we can transfer energy throughout a machine. So in this example, we're looking at how the energy moves from the pedals to the back wheels. And we know, and you'll know this if you've broken your bike chain before or it's come off while you've been shifting gears, if it's not properly connected, then that energy can't transfer and the machine doesn't work. So if your bike chain is broken, it doesn't matter how many times you pedal, you're not going anywhere, right? Another kind of energy transfer, pardon me, is gears. So this is a cassette tape. This is old school, you guys. But you can see that there's tiny little gears here. So they are like little circles with teeth. And as one turns, the other turns. And so this is how we used to listen to music. As you pressed play, it would connect to gears in the cassette player and it would turn the film basically to like create the music, right? And when you got to the end of this roll, the music would just cut out and you'd have to take it out and flip the tape over. But yeah, we also use gears in a lot of like big factory style machines. We use gears in clocks a lot as well, and even like hand like wrist clocks if you still have like old watches, right? So gears are really reliable and they're really good at transferring energy in big or small amounts. If we had bigger gears, we'd be transferring more energy, right? If we had teeny tiny gears, we'd be transferring just little bits, okay? And the last example is a transmission. So a transmission is a combination of gears and linkages together. So you can see that we've got some gears set up here for different gears of a car, right? So all the way from reverse to second gear, third gear, fourth gear. And so when you move the stick shifter, right, in the vehicle, what it's doing is it's creating a linkage between certain gears to give a certain direction to the car. And some gears are bigger, right? So they produce more power for the vehicle. So even if you were to switch gears into 4x4, you would get more power and you'd be able to drive over more things, right? Whereas if you shifted down into maybe second gear, that would just be like basic city driving, right? So the gears can transfer energy as well and change how we use the machine. So that's a little wrap up of topic one. I hope that that was helpful. As we head into topic two, we'll be looking at things like using math to calculate how much more of an advantage machines have or how efficient they are, how much faster they are at doing a job than if we just did it on our own. And then in topic three, we'll be wrapping up with just kind of taking a look at the usefulness of machines and some ethical issues around machines of the future. All right, have a good day.